is being recorded. Oh, did you all just hear that? Oh, okay, Brace. That's good. That I didn't know how we got that voice to happen, but we're not overly technical here at this little hooey that pulls these forums off, but we managed to do it. So we're all generally on mute and we'll stay that way through the presentation. If you have questions, you have something to say, just go and put it in the chat. I see things that people are already doing that. So Heather, let me know. Heather's here also helping out, Heather George. Let me know if there's something I need to know in the chat because I don't have the bandwidth to look at that too. And my name is Cynthia Welty. I'm with Surfrider Kauai. I get to serve currently as the chair of this exciting group that does a lot on the island. And we've joined forces with other groups to form the Kauai Climate Action Forum. These are held the second Wednesday of the month, just religiously, if I can say that. And between these three groups, I'm going to just show a little slide here. Here we go. These are the three groups that the chapters of Zero Waste on Kauai, of Zero Waste and Surfrider, and then a new group, relatively new, of powerhouse people who started the Kauai Climate Action Coalition. So again, we do these, we round robin once a month, and this particular forum is being brought to you by Surfrider, and we brought a speaker, Dr. Thomas Oliver, will be talking about in a moment. So stop share. That was a little fancy for me. Okay, there we go. So we, what will happen here in the forum is we're going to hear a presentation from Dr. Oliver, who we'll call Tom. Is that right, Tom? Yeah, go by first name, he's nodding there. And then we'll have a time for question and answer afterwards. And then we do this thing starting at 7 of just open discussion. We've wondered how it would work out, and it actually works out pretty well. We unmute, raise hands, and talk. And we have some really good discussions. I encourage you to stay, and that all winds up by 7:30. Wherever we are, we stop at 7:30. So our topic tonight is the impacts of climate change on coral reefs. And we're really glad to have Dr. Oliver, who's an expert on the topic, as I've learned through this. And you know, he's a humble guy by nature, but this is what he knows about. He knows a lot about coral reefs. He got his PhD from Stanford and went on into studying corals in American Samoa, growing corals. He's actually, his original field as an evolutionary biologist. So if you had time to talk to him, going into the evolution of corals is where it really gets fascinating. He's a little shy about saying he's an expert, but his work and his colleagues is on the cover of the current issue of Science magazine. So I want to just say, for forums like this, we might get a speaker like this over in Kauai. Tom would love to come Kauai, but we would be lucky to do so. So this is a pitch for Zoom and what happens during COVID, that we get to hear an expert on a very relevant current topic. If you have, I already said this, right? Put your questions in the chat, and I said it's being recorded. So I think we just want to go ahead with you, Tom, at that point, and go ahead and get started.
Sounds great. Hey, everybody. So it looks like we got about 40 folks here. Yeah, this is going to be as informal as we can make it. As Cynthia said, we're going to have plenty of time for a question and answer at the back end. But if there is stuff that I gloss over, I have a tendency to speak a little fast on occasion. So if there's something that you're missing, go ahead and throw your question in the chat. And Heather and Ruta are going to stop me and say, hey, we need to cover something. So feel free to do that. In the meantime, I'll go ahead and just get started. So let me go ahead and share my screen. So can everybody see it? Excellent. So thank you, Cynthia, very much for that introduction. Yeah, my name is Tom Oliver. You guys can just call me Tom. That's fine. And the talk for today, we've titled Finding Reef Resilience, right? So tracking climate change effects on coral reefs to empower coral management and restoration. It's a bit of a mouthful, but it really is what I'd like to spend the next half an hour or so talking about, is just taking the attention of this group, a group that has gathered, motivated by trying to better understand the changes in our climate and what ecosystems are doing in response to that, and really focus on the coral reef ecosystem, which is unique, important all around us in the Pacific Islands, and really one of the ecosystems most sensitive to and threatened by climate change in various ways, which we'll explore. But often these issues are heavy for those folks who are willing to listen. And over the course of the next half an hour or so, I would like to tell you guys a little bit about who I am, where I come from, what I do now. Tell you a little bit about the changes that we're already seeing in coral reef ecosystems. Tell you a little bit about what we see in the near future, talking timescale of the next decade and the one to follow. And sit with that for a while, frankly. I'm a big believer in hope. I'm a real optimist, but I think hope starts with understanding the scale of the challenges that we face in an honest way. And then, and only then, looking at the paths open to action and things that we can do. So we will talk about that. We'll move from challenges into pathways to action. And for me, that tension, that arc between the challenge and the potential starts in this place. So this is a shot of Ofu Island Lagoon in American Samoa. It's a very special place for many reasons. But one of the reasons is as we look from the ridge above the south coast of Ofu Island, you can see these small back reef pools. And those pools are separated by a few hundred meters, like a football field's worth of space. But in the summertime, during big low tide series they have, those pools get uncomfortably hot if you're a coral. 34, 35 degrees Celsius, that's 93, 95 degrees of water temperature, body temperature water. And each of those pools is slightly different in their temperatures, but each of them hosts a diversity of corals that are thriving in conditions that corals should not be thriving in. Those should be way too hot. That's fascinating. That's interesting. Why is that? And so as a graduate student working with Steve Palumbi's lab at Stanford, I spent 3 seasons out in Ofu, setting up labs, you can see right there on the beach, to actually test out, are these corals actually tougher? They are. Are these corals different to other corals nearby? They are. And really digging into the why of this. And it turns out these corals have locally adapted to this place, to these conditions, right? And if we go into the history of corals, there's a lot of history of them doing that. So that pattern of adaptation, that pattern of fitting their biology to the conditions is a real thing in corals, even though we know of corals famously as very, very sensitive organisms that are finely tuned. That is true. Anyway, that is a long-winded way to say that I come at all of the work you're about to hear, even the part that's going to make all of us collectively sad, from a very optimistic viewpoint, thinking of the changes that are happening on reefs right now are an evolutionary challenge for corals that have a fair amount of evolutionary capacity. And at the end of the day, it's going to come down to how fast coral populations can change. So with that, that was my PhD work. That was ended over a decade ago now, surprisingly to myself when I do the math. From there, I lived in Madagascar for a few years, chasing similar questions about corals and adaptation and resilience, working with some NGOs there. I then came to UH and helped design and teach their marine biology graduate curriculum at UH for a couple of years. And then about 2015, I came to work at this lovely facility. So working for NOAA, the National Oceanic and Atmospheric Administration, which is a multi-headed beast, many different line offices, from the Weather Service to charts and tides to running satellites and planes and boats. But I work for the National Marine Fisheries Service, right? And so we are concerned with making sure that US's fisheries are sustainable and productive. But we care not only about the fisheries, but also about the ecosystems. So my work for this institution is really working in what we call the Ecosystem Science Division. We have this wonderful facility, the NOAA Regional Center in Pearl Harbor, and it's both a wonderful office space. It has great laboratories to do the kind of science that I was trained to do. And we have a lot of access to, right there at the facility, to these white ships, which really are our bread and butter in our program. And all focused around the mission of providing sound science to enable informed and effective implementation of ecosystem-based management. And in my case, the ecosystem I focus on is, of course, coral reefs. But many people, many careers working at NOAA support that same mission, support the mission of understanding natural systems and understanding what human action can do to improve or mitigate challenges to those systems. Everybody from the atmospheric science technician sitting on top of Mauna Loa to the scientific diver, who's my personal colleague, right, to marine debris, whale responder, all over this. Many, many folks who are working mission focused. And I find myself very lucky to work with this diverse of a group. I also find myself very, very lucky. The thing that I get most excited about when I think about my job is the scale at which we work, right? The Pacific Islands is a very big place. The US affiliated Pacific Islands is still a very big place. And because of these ships and these surveys, I get to work at the scale of roughly half of the globe. We're actively engaged. So the umbrella that we're engaged in there is what's called the National Coral Reef Monitoring Program. That was signed into law in 2000 with the Coral Reef Conservation Act of 2000. It's currently up for reauthorization, co-sponsored by both Brian Schatz and Marco Rubio. And we will see if that passes this year. But you can see what this timeline on the left is the focus of our expeditionary work from 2000 to 2018. And basically it is, we go out to one area, usually an archipelago a year, and do surveys. We go out on this ship and we spend 4 or 5 dives a day, and potentially up to 4 different teams of divers out diving. In 2019, we did our most recent survey of the main Hawaiian Islands. And in the following year, we're headed off to the Marianas, but of course, COVID. And we're hoping to get back in 2022. But what do we do when we're out there? The main thing that I do is count corals. And I put those in big quotes because we do a lot more than just count them, basically. We engage in a geographically comprehensive survey of all hard bottom habitat between 0 and 30 meters. We lay out transects and we identify corals to species mostly, but genus in some cases, and document their size, their density, and their condition, specifically looking for disease and or bleaching states. And in each of those cases, we also take imagery. So we're taking downward-looking photo quadrants, right? So we have basically pictures of the bottom to archive those in time, and we use that to document patterns of change over time. We also count fish, right? So using both what we call a stationary point count and towed divers, where we tow a diver behind a boat, our divers go down and document the number and sizes of fishes of different functional groups, which lets us get to actual biomass. So like how many fish are on this reef and total how much biomass of, say, herbivores are on this reef, which is a very ecologically important thing, as we'll see as we move forward. We also track climate drivers. And what I mean by that is mostly temperature, ocean acidification from seawater chemistry, and what we call coral reef accretion or erosion, right? So in each of the islands we visit, and we visit over 40 islands over the scale of our survey, we lay down transects of temperature loggers. So not only do we have satellite surface temperature, but also the temperatures that the corals are actually experiencing across a range of depths. We randomly sample for calculating dissolved inorganic carbon and total alkalinity, which are sort of 2 points of entry to figure out how the ocean is acidifying or not in a local context. And then we also have a number of things that we do in fixed sites where we follow the patterns of how much coral skeleton is being added or removed from a place, which is of course very sensitive to ocean acidification. We call that accretion and erosion. We track all of that as well. We also are always looking for new tools to make our job richer and more efficient. And this is one of those. This is called photogrammetry, or structure for motion photogrammetry, if you want to be long-winded about it. But it's a really exciting new technique that we're now applying across the whole scale of our surveys to really freeze a large section of reef in time and allow us to revisit and even track individual colonies over time. With all of that science that we're constantly doing, constantly generating, our other role, of course, the most important role that we have is to take all of that knowledge and immediately inform management, right? So that is the Fisheries Management Council, the federal managers at NOAA. So very clearly, I am not a manager. I am not a policymaker. I am a scientist, and it is very clearly defined in my role that my job is to inform, not decide, right? And so when it comes to all of these guys, I am here to tell you what's happening and potentially run scenarios about what would happen if, but should is not in my vocabulary when it comes to my professional work. But we work with the federal managers. We also work with state and territorial managers. So Hawaii DAR, Department of Marine and Wildlife Resources in Samoa, the Division of Fish and Wildlife in CNMI, and the Guam Division of Aquatic Wildlife Resources, the folks who actually do the hands-on management of our reefs in the region. And we also take communication and outreach really as a really important focus of our job. So we write status reports of all of US reefs, or there's a version of that that's just for Hawaii. I also really focus on coral resilience, as you hear throughout the talk. And so I've generated with my colleagues a number of reports focused on our best assessment of the resilience of particular areas. And if you want to know what's going on in Kauai, you can look up that. If you guys want those references, please ask me. But both of those documents serve to answer the question, how are our reefs doing? That's what everyone asks me. When people find out I'm a coral reef biologist, they have this sense of unease that comes over them. Oh, you're a coral reef biologist. So how are the reefs doing? And the answer is, it's serious, right? Global threats to coral reefs are serious and getting worse. In the face of that, though, there are many high-level reef biologists who would say, and there's nothing we can do in the face of it. I disagree very strongly. I believe local management matters, and I believe we have the science to support that contention. And I believe there are paths that we can make a difference by acting a certain way, in addition to dealing with the global problems. So what are these threats? What are we talking about? Well, there is a buffet of threats. There is an overabundance of choice when you want to talk about threats to coral reef ecosystems. But you can roughly break them up into the short-term and local threats, like poor water quality, overfishing, especially of herbivorous fishes, outbreaks of coral predators, like crown of thorns, and the longer-term, more globally linked threats, like the increase in severity and frequency of marine heat waves that lead to catastrophic coral bleaching, increasingly common, increasingly destructive. Or a longer-term press, what I consider a press stress. So one of these stresses that just keeps slowly getting worse over time, ocean acidification, which is a very serious threat to an organism that builds its skeleton and its life out of a material that is very quick to dissolve in acidic conditions, calcium carbonate. And finally, disease, which really has been the death knell of a number of ecosystems, coral reef ecosystems, especially in the Caribbean and the Atlantic. But they're often, although it is kind of a local thing, I put them in this global column because they're often tied to events like heating, right? And often the etiology of the disease is determined by temperature of the water. So a bunch of challenges here. And as this is a climate forum, I'm going to be focusing primarily on the climate drivers. But it is core to my science and core to my understanding of these problems that all of these are interrelated, right? And that there are moves that we can make locally that affect the way that local ecosystems respond to the global threats. And in particular, as you'll see, the dynamic between corals and algae is a fundamental issue on reefs, and one that apparently matters in the face of bleaching. We'll talk about that later. So, a few minutes in, it's worth going back to basics. I know this is a climate forum. I know you guys think about these issues a lot, but I find, even for the issues that I'm most passionate about, going back to basics often helps me think about a new problem, a new way. So I'm going to go ahead and take a few minutes to do that. What is the fundamental problem when we're talking about climate driving problems? We're talking about anthropogenic carbon flows. To put it in the terms that the global carbon budget uses, what this means is basically what humans have done in the past. And let's take a long view on this. Let's go over the past 170 years. Go back to pre-industrial baseline, which is 1850 or 1860, thereabouts, sort of before we started burning fossil fuels in earnest. And over that time period, from fossil fuel burning and land use change, we mobilized about 650 gigatons of carbon. That's the root of the problem. Where did that go? Let me pause for a second. A gigaton is not a metric that most people have any real personal relationship to. Let me just give you a sense of that number. A gigaton is 1 billion metric tons. It is roughly equivalent to the biomass of every animal on the planet except humans. 1 gigaton. So we're talking 650 of those over the course of 170 years. So it's a big number. Where did that end up? Well, of all of that carbon, about 40% of it ended up in the atmosphere. We can measure it today. It's still there. About 30% of it ended up in the ocean. We can measure it today. It's still there. And about a quarter of it ended up taken. It was taken up by land sources. So things like soil carbon or trees, right? It came back. So basically the land use emissions and the land uptake nicely balance, but those reservoirs that are still open in the ocean and open in the atmosphere are the problem, right? That atmospheric fraction, that 40%, is what is driving, in large part, the greenhouse effect and global warming. And as a distinct problem, that 30% that ended up in the ocean is what is driving ocean acidification. That's the root of the problem. And solutions to that root of the problem need to address that problem. We can talk about geoengineering and my opinions about it later on. Anyway, evidence of that, right? I like to keep it to evidence. I like to keep it to observations even before we move to projections, not what is going to happen, what has already happened. This is a nice tie to Hawaii. So the Mauna Loa Observatory started in the 1950s measuring atmospheric carbon. And being way up there, they get clean access to well-mixed air, and they've tracked it over the years. And what we've seen over the years is a steady increase, right? In 2020, we hit higher than we've ever seen, 414 parts per million. The most recent data came out for 2021, sort of assessing the sort of seasonal variability. 2021, it's even higher than that. Even though emissions went down a bit during COVID, the average continues to climb. I think it's worth noting, just to give a little bit of personal sense to this, one of the sponsors of this event with the Climate Action Group is 350.org. 350.org refers to this metric, right? And right there in the 1990s is about where we were, 350. We are now 414 and higher. So what does that mean? One of the most direct effects of that atmospheric carbon is the increase in global mean surface temperature, right? GMST. And again, observational data from the 1950s to 1990 set a baseline. Above that baseline, we have already gained about a degree of global mean surface temperature. A few years ago, nations met in Paris to set an objective of avoiding catastrophic climate change by keeping the global mean surface temperature below 1.5 degrees. We're pretty close to that already. How close? One way of visualizing this came out of Stanford, and I really like the visualization, so I use it. It's basically a bucket, and the y-axis of this bucket is going to be emissions, cumulative emissions. There's a certain number of emissions that you can take before the bucket overflows and you miss your 1.5 degree target, right? So 100% means we hit 1.5. How do we do? How have we been doing? As you can see, the years go on. USA, the EU are primarily the contributors. The rest of the world starts to grow towards the end of the 20th century. India and China come on. And as of 2020, we had about 8% of that bucket left to fill before we come over, or less than 10 years at current emissions. Right, so we are very, very, very close to 1.5. And if we actually just project our current policies without major changes, we're not stopping at 1.5. We're looking at around 3.5 degrees of warming. And even with the much more ambitious, currently stated net zero targets that many people are throwing out, which is very exciting and I love hearing about. Even with that, there's enough warming in pipeline already that we're talking somewhere around 2.5 is the current estimates, right? So major global scale changes are afoot. But corals don't care about that, to be blunt. Corals don't care what the global mean surface temperature is. Corals care very much, though, about what their local temperature is and what marine heat waves can do to them physiologically. The phenomenon that occurs after a global, after a local marine heat wave is commonly referred to as coral bleaching. It looks something like that. White coral that shouldn't be white ought to be brown. And what is that? What is that about? Well, a healthy coral, what is a coral? It is an animal. A coral is an animal that secretes a calcium carbonate skeleton, but that animal has this amazing trick of living its life like a plant because it literally has microscopic algae, dinoflagellates, that live inside its cells. They're intracellular symbionts. They're commonly referred to as zooxanthellae, as they are in this image here. And normally, the plant is sitting there, living there, feeding off of the carbon like it's got its own internal garden. And most corals live mostly by the energy that their zooxanthellae make. If the temperature gets too hot, and not that hot, really, about a degree above long-term summer maxima is what our rule of thumb threshold for bleaching is. As that water temperature increases, that symbiosis breaks down. And the zooxanthellae leave the tissue, and they take their color with them, and they leave a transparent living animal covering up a white skeleton. So a bleached coral early on is still a living coral. It's still a live animal. And given the opportunity, if that water temperature returns to normal or wasn't that severe, it can brown up again and become a healthy coral and live on its life. However, if that temperature stress is prolonged or severe over the timescale of days to weeks, that coral will die. And we're seeing this play out increasingly on reefs. And increasingly is what this slide is meant to show you. So these are what we call degree heating week measures, right? So that's a how bad was the heat wave metric, right? 0 is there's no heat wave. 4 is we expect mass coral bleaching, but not a lot of death. 8, we expect mass coral mortality. So this is a time series using satellite data from NOAA's Coral Reef Watch from 1985 to 2021. Very recently pulled this data down. And what it shows is basically, this is a new phenomenon for Hawaii. The first scientifically recorded bleaching that anyone ever wrote down and published in a paper was in 1996. It's barely a blip on this map, right? Then trucks along 20 years, even longer, we hit 2014. In 2014, we saw significant heating, we saw much bleaching, and everyone woke up and got busy monitoring and measuring and getting ready for the next year, 2015. In 2014, we didn't see a lot of mortality. Then came 2015. And in 2015, we saw major effects of bleaching, including major mortalities. A couple years later, we had a few minor blips in terms of warming. In 2019, we saw another major bleaching event, though it looks as bad as 2015. In the end, it was not as bad. But when we look, and when I say major effects, if we compare our data from 2013 to 2016 in terms of coral cover, with that bleaching event right in the middle, really both of them, but the big one was 2015, we can see significant declines in coral cover across much of the state. You can see Kauai did okay in this. This is largely because they were not exposed to big temperatures in Kauai, but for West Maui, West Hawaii, we saw major declines. And if we look across the entire state, we lost about a third of our coral cover in that one event. That's a number that sits with me, right? That's a number that feels like wildfire status, thinking about burned hillsides, a third. And we did not see this before, right? 2014 to 2019, we saw 3 major events over the space of 5 years. Our friends at the Coral Reef Watch over in NOAA in Silver Spring, Maryland, generate predictions of the bleaching season. They have about a 4-month window where they feel confident that they have some skill to predict. Those predictions just came out for this season. And what you're looking at is a heat map of probability of an event similar to the 2014 scale, right? With orange being, yeah, it's likely going to happen. And you can see for much of the Hawaiian Islands this year, we are expecting an event on the scale of 2014, which would take it to 4 major events over the course of 6 years. When before that, the one before that was 20 years before and minor. So given those thresholds, given our understanding of the relationship to temperature, we also have increasingly sophisticated projections of temperature, of what's going to happen between now and 2100. And one of my colleagues, Jeff Maynard and Ruben van Hooydonk, have taken those values and come up with a pretty intuitive estimate of when things are going to get real bad. And that is what we call annual severe bleaching. So think of that 2015 event in which we lost a third of our corals. That's a severe bleaching event. And what they do is they project temperature forward using the new models that are just coming out from the Intergovernmental Panel on Climate Change, and say, okay, in what year should we expect every single year to be as bad as 2015? Not when is it next going to bleach, but when is it going to do this every single year? And if you look at that value is the color there. And if you look at the whole Hawaiian archipelago, in Papahanaumokuakea, we're expecting, starting around 2030 and a few years thereafter, to be seeing this scale of an event every year. That's within the next decade, maybe a little more, 12 years away. If we zoom into the main Hawaiian Islands, there's a bit of a sad and a bit of a hopeful story here, which is there's a really big difference between windward side and leeward side. And this is very new. These data came out weeks ago. And what it tells me is that on the windward side, where it is traditionally about a half a degree cooler, and given that we're expecting trade winds to not be as strong in the future, between those two things, we expect warming to be a little bit more severe and corals already being adapted to something that's a little cooler. So the effects will be worse. And again, similar timescale, a little bit later than Papahanaumokuakea, so in the mid-30s, right? So maybe 15 years out. But on the leeward side, pushing to 2060, maybe 40 years, right? So that's both very, very worrisome and also an intriguing opportunity from the perspective of someone who's thinking evolutionarily, because there is both challenge and potential refuge in these spaces. And we'll come back to that later. Okay, on the warming side, that's the scale of the problem. It's big, it's real, it's happening, and it's happening not by 2100. It's not grandchild timescale. It's you in 10 years timescale, right? It's before I retire timescale. And we need to sit with that. We need to understand that. And we need to let that set our priorities. Good news is there's stuff we can do. And that's what the science paper that Cynthia referred to was all about, was trying to understand, okay, given that it's going to be bad, is there stuff we can do? Does it make a difference? And the answer, the top level answer to that is yes, it does. So distilling the results of this paper are, if you look at hundreds of sites around the globe, right, in fixed sites, and you look at areas that were exposed to one of these heat waves, and you look at corals before and corals after, and our big response variable here, the big metric of change is how much did it change? Did it get worse, or did it get better? Or did it stay the same before and after that heat event? And when we do all the math, we do all the models, it says change in coral cover after a marine heat wave depends both on the severity of the heat wave, okay, I expect that, but also on local conditions, especially on macroalgal cover, right? And this is a correlational model, correlation, causation, take it with a grain of salt. But when we look at many, many, many sites, these are the patterns that we see. So the core result is represented in this graph. I want to orient you to it before I throw a bunch of complicated data on it. The y-axis is that metric, change in coral cover. Above 0 is good, below 0 is bad, getting worse. And the x-axis is percent macroalgal cover. 100% mean there's nothing but macroalgae. 0 means it's all hard bottom coral kind of stuff, right? And these are the data, right? And what this says is that coral loss from heat waves worsens as macroalgal cover increases, and this effect is stronger in major heat waves. Walking through you a little bit, these blue ones are minor heat waves, right? That metric we used before, degree heating weeks, those are around 1, right? Like enough to record as kind of hot, but probably not going to do a whole lot of damage. And then the orange ones are above 6, which is super hot, like basically severe 2015 kind of hot, right? And what it shows is that when you have more macroalgae on the reef, the effect on the reef is worse. And if it's a major heat wave, that slope is even steeper, right? That's the sadder way to put it. The other way we could put that is that coral loss from heat wave lessens as macroalgal cover decreases. And this effect is even stronger in major heat waves, suggesting that if we manage our reefs well and we keep them in a state that is supportive of coral growth, right, that even response to heat stress can be mitigated. You got, like, the heat stress matters. You can't say, it doesn't matter, it'll take it. But things fare way better than we expect when the reef is in good condition. And I hope that's a hopeful note. With that, I want to transition to ocean acidification. There's a lot of science here as well. It's not easy to summarize, but I'm going to do my best. So similar to that atmospheric trend, we have an observational trend of coral reefs that, again, starts in Hawaii. Station Aloha, just north of Oahu in this map over here. In 1989, we started taking seawater samples there and recording what the pH is. And every 2 weeks since then, we have tracked the decline of that pH. And over the course of 1989 to 2019, we've seen just shy of a 10% increase in acidity. pH units are weird, I don't want to go into them, but it's about 10% increase in acidity. And based on that and some modeling, if we go all the way back pre-industrial, we expect about a 30% increase in acidity, right, from observational data. So the ocean is acidifying. We can see it happening. But it's not happening the same everywhere. So let me introduce another idea. There's something called what I would call reef-relevant ocean acidification. And the metric we like to use is aragonite saturation state. Aragonite is a particular form of calcium carbonate. Corals build their skeletons out of calcium carbonate. This is basically how much calcium carbonate is in the water available to corals to calcify. So on the end, up by 4 and 5, it's a very easy place to be a calcifying organism. You can build your skeletons quite well. There's a lot of raw material. There's a lot of lumber lying around if you want to build a house. As you move down this scale, down to 2, 1, or even less than 1, there's a lot less of that calcium carbonate around. It's a much harder place, and it's the kind of environment the corals really have not adapted to well. So back in the day, 1860, pre-industrial, our numbers are all around 4, higher than 4. Very great place to be a coral. As we step forward to 2014, that number drops, centered more around 3.5. But you can see not all places are equal. Up here in that yellow circle, Hawaii, it's getting harder to be a coral. And the time scale of the next few decades, it's getting even harder. Again, about a 0.5 point drop. And this is particularly true in Hawaii, and even worse in Papahanaumokuakea, the northwestern Hawaiian Islands. It's right up on that latitudinal band where it's getting very hard indeed to be a coral. And again, current projections at 3.5 degree global surface mean scenario, by the end of the century, it's extremely hard to be a coral. We are measuring this exact parameter, not just modeling, but measuring across all of these islands as part of the National Coral Reef Monitoring Program. You can see the scale in the upper right, and you can see the main Hawaiian Islands sort of are somewhere around the middle of that scale, around 3.5. You can see, however, there are many places that do much better, especially in American Samoa. It's a wonderful place for a aragonite saturation state. But again, in the northwest, Papahanaumokuakea, those values are much, much lower, right on the bubble of being not a great place for a coral to live, chemically speaking. So it's worth saying, though, for a living reef coral, ocean acidification is like your rent going up. This is a belabored analogy, but bear with me. Corals calcify internally to themselves. There's a skin of tissue over the place where they calcify. They secrete their skin, in their skeleton, inside themselves. So being in an acidic environment just means you got to do more pumping of ions to make that all work. And it's basically a problem you can physiologically throw money at, right? So all else being equal, you're living a wonderful life, you can make it work as a coral. It's a very different thing for the reef itself on which you're sitting, which does not have that skin over it and is exposed to a balance of production of reef material and removal of reef material through dissolution and bioerosion from urchins and sponges and stuff. And when OA stresses are low, you're in a net production state. You're making reef. Life is good. As that OA stress goes higher, your production goes down, your removal goes up. And it's these loss terms, what we call loss terms, removal, that many people are really concerned about being the real impact of OA. And there are analogs of this in the Eastern Pacific, like out by the Galapagos. There are corals that live there, but they live on basalt rock. There's not a reef for them to sit on. And that's a fundamentally different coral reef ecosystem than what we have in the Central Pacific, where most of the benches are actual reefs. We measure the secretion a bunch of different ways. Remember those like fixed sites I told you about? One of the ways is by literally measuring accretion. We put out fouling plates. We come back 3 years later. They get fouled with some stuff. Some of it's carbonate, some of it's not. We measure the carbonate fraction. And then we plot it in plots like this. So the x-axis here is that measure of how much carbonate is around. On the right-hand side, it's lots. On the left-hand side, it's not very much. And then the y-axis here is whether you're building reef effectively. And what you can see is that the main Hawaiian Islands are those blue circles right in the middle. They're okay, but they're still threatened. Whereas the green circles, you can see, are lower than that, having a pretty hard time even getting positive in their net accretion. That's where I'm going to leave OA. If you have more questions in the discussion, let's talk about it. But I do want to get to differential resilience, because this is the core of what I do and why I'm motivated to do it, is that the tools to monitor for differential resilience, areas that resist and recover and areas that don't, are getting dramatically better. So let me pause on resilience for a second. Resilience refers to the capacity of a system to resist and recover from disturbance and maintain structure and function to provide ecosystem services. That's the definition straight from NOAA. And basically it means if you're faced with disturbance, do you return to your original state or do you change? And what we're looking for here are areas that differ in that capacity, especially looking for those areas that are more resilient than we would expect, like those areas with low macroalgal cover reefs, as we saw in the science paper. And we want to know where there is differential resilience. Excuse me. We want to know which colonies have resisted or recovered. We want to know why. And we want to know how we can use this to guide information. And I've got a few more slides, Cynthia. Is that okay? Or are you getting impatient? We're good? Okay. So
it's so interesting, Tom. Yeah. And
okay.
We're doing good.
Okay, we're doing good. So the tools I'm talking about are some of those that I gave you a little teaser for above, and they're mainly imagery tools, right? So I talked a little bit about photo quadrats before. We can just take a picture of the bottom and it tells us roughly what's on the bottom. But these days we have moved to a whole new technology that lets us capture large areas of the reef, right? And look at a whole diversity of metrics, from structural complexity to actually tracking individual colonies, right? At a whole new scale. So this is what's called structure for motion photogrammetry. And it aligns hundreds to thousands of pictures in a specific site. And it allows us to build models of the reef. And it's getting more and more traction as a technique globally. And it leads to beautiful models like this one. This is not Hawaii. This is a site in Palmyra. But as it zooms through, you can see that this imagery with some human annotation on top of it can return some really important information. We can get size structure information, we can get interactions information, we can get diversity information, all from original imagery that we have saved, right? So we know what that reef was like when we had it. But where this technique becomes very strong is when we image the same area many years in a row. So what you're looking at here is that same site in Palmyra in 13, 14, 2015, 2016, and 2017. And as it slides across, it's a year advance. And in 2015, there was also in Palmyra a major bleaching event. And you can see individual colonies that grow, that bleach, or maybe not. After they bleached, maybe they die, maybe they don't. But we can track that response at an individual level. And we're doing that. And then we're now doing it at scale. So we have about 307 of these plots established. In our most recent cruise in 2019, we repeated the imagery, about 100 of those, and we're going to continue doing this as we move forward. And it has the potential to expose differential resilience like you're going to see here. So scrolling through time, this is actually Hawaii. In November 2015, that was the bleaching event, and that was same species, same reef. That lower colony recovered, the upper colony partially died. Looking at these two Posilopera, the same thing's going to happen. The one on the right bleaches and dies. The one on the left doesn't. Those are the same species on the same reef. Totally different responses to the stress. And what we want to know is why. That is the pattern of differential resilience. And using these new tools, we can track that differential resilience at colony scale, at site scale, at reef scale, at island scale, like this nested scale, and really focus on why. We can also actually measure recruitment, growth, and death at that colony scale and build models of populations so that we know how they respond to different environments. And it also gives us what we call a strong coral address book. So if you ask me after an event, where are the top 5% coral that responded well to that event, I can tell you where they are, down to a millimeter, because I have it imaged and I have that image geolocated, right? And so we can go out and we can potentially get those corals for genetic analysis or get those corals to seed restoration events. And it's a really important part. So wrapping up, the global stresses are real, but local management matters. Simple things like keeping the water clean, simple things like making sure there are enough herbivores on our reefs, simple things making sure that we keep crown of thorns and disease outbreaks in check matter. And there is more that we can do aside from just fish and water quality. Those are important, those are critical. But people have been expanding and getting creative and thinking about more active interventions. The National Academy of Sciences just had a 2-panel review on this, a 2-workshop volume. NOAA adopted a number of those, and there is now this table of what we call active interventions. Everything from pumping cold water onto our reefs, maybe. Manipulating which algae are in those reefs, maybe. assisting gene flow, right? So supporting areas that do have those more resistant corals, those stronger corals, and making sure those genes get into the populations at appropriate times. And a whole bunch of higher risk, higher reward potential interventions that we are now experimenting with and proving out, and kind of opening the universe that we're thinking about. And with that, I'll stop. So thank you very much. And I'm sorry for going so far over time, Cynthia.
It was good, Tom. And I was going to say a few moments about Surfrider, but I'm going to skip that. Surfrider's doing a lot of things. If you want to learn about it, go to our website, or you can get in touch with me and I'll put my contact in the chat. But I think we should switch right into questions. I've seen some interesting ones go by. Heather George of Surfrider is going to select them and let us know. What should we hear about, Heather?
Thanks, Cynthia. Yes, lots of great questions coming through here. And one of the first ones was, you mentioned, Tom, that we could get access to reports. Someone was asking for those about the Kauai reefs. And so I see you put your website up there, or your email. So I think if anyone wants to grab that, take a screenshot or something, but we can put that also in the follow-up. And then also someone was asking, Charlie was asking, can you share these slides? Are you able to share them, or are they stored somewhere on the NOAA website, or is there any access to these?
These slides are custom made for this event, but I'm happy to share them. Yeah, so how about I send them to Cynthia, and then Cynthia, you can distribute them?
Absolutely. And this event also is being recorded. Several people have here said, great presentation. Wow, I just learned so much and I'd already seen it.
Yeah, I feel the same way. And then Chris, who had a bunch of questions here, one of those was, do you leave instruments in the water on the coral or satellites to record continuous data points? I think you kind of talked about that. Or is the data collected periodically and the data filled in between samples?
A little bit of both. For the temperature loggers, they're down and they're logging every minute or so. The cost of maintaining a network that actually has telemetry that would tell us back in Honolulu what the temperature is way more expensive. So we put them down. They last for 3 years. We pick them up again and replace them. And so we have continuous time series by the minute, but we only get the new data every 3 years when we can go pick them up. In terms of other instruments, we would love to monitor all sorts of stuff that same way, but light sensors get fouled. pH sensors, they haven't improved a lot, but they don't have duration for 3 years, right? So we do a bunch of instrument package deployments while we're in a region, and we'll leave it down for, say, a month, but then pick it up on the way home. So we do a bunch of those kind of instrument deployments. There are some cabled observatories. There's a bunch of buoys around Hawaii, and now one that we maintain in American Samoa that does telemeter, and those track ocean acidification. There's a couple of them in Kaneohe. There's a couple of them on the South Shore of Oahu, and there's one in Tongateli Bay in American Samoa. But for us, the in situ work, we do a lot of work with satellite, and then the in situ work is mostly these kind of long-term deployments.
I presume that that resilience, the advancement, the scale where you watch it change over time, the more data you can pump into that model, the better it comes out at the other side, right? So
yeah, it does. And we found we still primarily rely on those degree heating week estimates that come from the satellites for the bleaching models, right? And we found there are a number of other parameters that we can get that make those models way better. And we're working on those. Publications will be coming out soon.
Cool.
Great. Yeah, I've got a lot of questions coming in here, so we'll try to power through some of them quickly. Are there any particular conditions that you might say affected Kauai specifically in 2015 so that we didn't have as high of a death situation versus the other?
Yeah, let me see if I can show you the primary one. Can you guys see that, or did I stop sharing when I snapped off?
Oh, you're good.
We can see it.
Yeah, you're good. You can see it. Good. So these are heat maps of the stress that happened in 2015 and 2019 respectively. And you can see for Kauai, compared to the rest of the main Hawaiian Islands, they just didn't get that exposed, especially in 2019. But they were moderately exposed. Even though 2015 had that big spike on my graph, that's for the whole island chain. Whereas Kauai itself didn't get, I mean, it got hot. It certainly recorded, right? It's in the just shy of 6-degree heating weeks, which is a considerable event, but it wasn't as bad as the 14-degree heating weeks at the main Hawaiian Islands, so that Big Island. So that's a major effect. About Kauai. And also Kauai has had its own struggles really with coral disease has been a major threat to Kauai. So some of the impacts of sort of getting the reefs from sort of these fully developed reefs that got bleached like crazy and dropped majorly, the baseline levels were a little lower on Kauai. So we didn't see a huge reduction, but.
Great.
Yeah.
Okay. Sort of maybe related.
One more, Heather, before we go into wrap up this portion, and then we'll still stay together.
Yeah,
so much. Yeah. Okay. Any correlation between bleaching and hurricane season predictions? That's an interesting.
Yeah, there kind of is and isn't. Usually the role of a hurricane, ironically, is to ease off the stress from bleaching. Well, approximately, right? So like, in the Great Barrier Reef, there was a major event that was coming, and a hurricane happened to sweep through the southern end of the reef, and it mixed up all this ocean water and basically cooled things off. But the increasing severity and frequency of marine heating events is correlated to the same factors that are driving hurricane seasons to be worse and more severe, right? So on some level, when they're like, the hurricane blows through and eases off the bleaching season, that's great news. But the fundamental driver behind both of those trends is the warming of the oceans, right? So they're also correlated in that much larger scale sense. The larger scale sense, honestly, is much harder to establish climatologically and statistically than the other ones. But
okay, well, good. Listen, we want to wrap up this portion, stay on time, because and let people go as they need to. And we are going to, you can stop sharing, Tom. We're going to move into the discussion time and Chris kind of launched a little early with that, where you can just go ahead and ask a question. It worked real well. That's it. You kind of modeled. That's how
I can't seem to help
works.
myself. Sorry about that.
Or just raise your hand, ask a question. Tom, you should know we got some scuba divers here online for the Scott Bacon's group who goes out and takes care of the reef, and they're interested to talk to you. I also want to say at this moment to give we do these forums monthly, and they are interesting. As you hear, the next one is from the Kauai Climate Action Coalition, and they're hosting a talk on regenerative agriculture. We're going to see a movie I've heard good things about called Kiss the Ground. So you get free access to this movie ahead of time. You watch the movie, by yourself with your own popcorn, and then we'll have a discussion about it. So that's on July 14th, a month from now. And with that, this is our moment to say thank you, Tom, in a more formal sense, and then we'll just get into a more relaxed chat. So if you want to unmute and clap, we'll just really thumbs up. We get a lot of, if you probably haven't looked at the chat, Tom, but there's a lot of, we really liked the talk. People really liked it.
Yeah, I'm scrolling through, and there's a lot of really good questions in there too. So I hope the discussion is going to be fruitful.
Yeah, yeah. So we'll take another half hour of discussion. Rudy, you want to say something?
I just wanted to ask, Tom, would you be willing to respond to the questions and then we can send them out with the recording?
Sure. Yeah. How about if I can just copy and paste the chat, I can write out responses after, or do you want me to go through right now? I assume
no.
We'll send it to you.
Yeah. Send it to me and I'll write out responses for sure.
Okay. Well, good. Yes, it makes sense. Yeah. Okay, so so the way this works, open discussion, I said it briefly, is maybe you can kick us off, Heather, with grabbing another one from the chat, but then after that, people can just raise their hand and ask a question that we didn't get to or something else that came to mind. Oh, and to raise your hand, you can do it like this. And there's down in the reactions at the bottom of your Zoom screen, there's a little reaction thing, and you can just click on that and raise your hand. So raise a digital hand. Okay, Heather.
Right.
What you got?
Yeah, sure. There's, like I said, lots of great questions, and I'm just going to pick up where I stopped in the list here at 6:40 p.m. It looks like Kira was asking, would introducing corals that are more resilient to warmer temperatures to our waters be an option? I know you kind of laid out some of those particular options and so many things that we could do, but would that be helpful or feasible even?
Yeah. I'll say helpful. I'll say feasible. I'll say risky. One of my favorite papers is written by a friend of mine. I didn't know that it was coming out when it came out. I read it. I was like, oh, Cheryl, that thing is amazing. Basically, what she did was studied, because of the work that Steve Palumbi's group did in American Samoa, we now literally know for at least one species the architecture of the genetics of elevated thermal tolerance, right, in a species of coral. And so they found a different population, higher latitude population, where they surveyed the population and found none of those alleles, right? So a population that was not exposed to high temperatures like they are in those pools in Samoa, just didn't have the genes for making tough corals. And they teamed up with a set of evolutionary modelers, and they said, okay, let us put these populations through their paces in a simulated way and say, okay, can this population basically make the evolutionary leap given those genes in their population, right? And the answer was, in the worst case of bleaching, the worst case of scenario projections for climate, they're all toast. But in moderate cases, in not the best case, not the like we do everything perfectly, but the sort of middle of the road cases where we kind of get our act together a bit, the population with heat stress resistant genes, even at low frequency, do just fine. The population without them does not, unless you move a few, not even a lot, but a few of those corals that have those genes into the population early enough and they survive long enough to mate with those corals, you can perform something called genetic rescue, right? Where that population that didn't have those stress resistant corals before now can also survive that moderate level of climate change, right? So that's extremely exciting. My old advisor, Steve Palumbi, who saw this result and was a co-author on the paper, is deeply terrified by the result because moving corals around at really any distance is a risky endeavor when we've seen the amount of disease and disease spread that has happened in the Caribbean that has tanked entire ecosystems, right? So moving corals around kind of at all is a scary proposition. But it's hard to argue with the idea that, like, if we, this is a hard thing to say. Let me just see if I can frame it correctly. Restoration, where you are the one planting every seed that turns into a coral on a reef, is crazy amount of work in terms of cost and labor. But a system where you can put out a few strategically selected individuals that become part of the process of natural selection is a real chance for achieving scale with a small amount of effort if the risk to reward is well balanced.
Sounds not easy.
Yeah, sorry, I know that was a very
that's
deep
the summary.
Thank you for carrying through with me on that. If you want me to rephrase that in any way, I can. Short version is moving corals around, taking populations that are resistant into populations that don't have those genes could be a very, very good thing. But it is also not without enormous risk.
And Heather, you just keep rolling. We've got somebody with their hand up and you got questions. So you just keep going.
Well, sure. Amy was asking about, could we put more of the calcification monitoring units, or what is that? The CAU, calcification accretion units in the, I guess, MHI, Main Hawaiian Islands. Could we do that?
Yeah, we have a fair number of them out there already, and we're writing them up. There's one paper out that's sort of just describing patterns, and we've got another paper that's sitting on my desk that needs to get out, that basically models the drivers of that accretion and projects into 2100 based on scenarios, right? So we've got a pretty good network of them out, and we're collecting that data. And I mean, they're relatively inexpensive to install. But hauling them back and processing them carefully takes some equipment. It's not, again, wildly expensive, but if there's like a master's student that we're excited about applying that stuff, we could talk about it for sure. We have all the methods and they're public. So if you want to do it and you can get the permits to do it, great. Happy to help.
Okay, great. Right. And it just takes some funding too, right? Yeah.
Yeah.
So, okay. How about we read about reefs recovering when left alone from human disturbances? We've all read about those situations. And is it very true? And if there are fewer people in the water, like last year over here, and there were a lot fewer tourists around, obviously on the Hawaiian Islands, has there been any evidence of recovery when there's fewer people overall?
So the question made me sigh deeply because it made me think about Jarvis. Many people don't know about Jarvis. Jarvis is an island in the middle of the Pacific. It's right now down by the equator. Some folks may have heard about it because there were actually Hawaiian colonists that the US government stuck on Jarvis during World War II to claim it. And it's a fascinating story. Under a Jarvis moon is a fascinating, I think you can get it on YouTube. It's worth looking at. But Jarvis was one of these places that, I don't like to use the P word, but it was pretty close to pristine, right? One of these places not heavily fished. The biomass of predators was enormous. The coral cover was high, and the reefs were complex and stacked on each other. During that same period of sort of 14, 15, 16, the reefs in Jarvis experienced globally driven heat stress that just broke the degree heating week scale. Like it just broke it. It was like 38, right? And 98% of the corals on Jarvis straight up died. Right? That's one of the most remote reefs in the entire world. And climate change was enough of a stress that it just broke it. And it is now a 1% coral cover reef. That said, I'm sorry, like one hand, other hand, that said, when we look at bleaching patterns in 2015 and 2019 around the main Hawaiian Islands, one of the things we look at is this metric of sort of tourist density that comes originally from Flickr posts. It turns out Instagram post density is a lot harder to get hold of, but Flickr was very open with their data, so we made good indexes of it. And it's a minor effect. Like you can see it and it makes a difference, right? But it's one of those things that sort of makes a difference at at the threshold of our ability to tell in our modeling, right? So keeping tourists off the reef, probably a good thing, especially during the heat of the bleaching stress. Is it enormous and should I scream from the rooftops to stay away from that coral? Like, it's not huge.
Great. Okay. Yeah, we've still got lots of questions pouring in here. And if we don't get to yours, I know some of you guys are raising your hand. We'll get to them and just put them in the chat. We'll get back to you.
Oh, yeah,
and Tom will have a lot of homework.
Let's get some of the hand raisers. I know Steve's had his raised for a while there. So Steve, what you got?
Oh, aloha. Thanks for calling on me. So Dr. Oliver, I really appreciate your time in coming in here and talking to us. I just had a question about something you mentioned a moment ago about the alleles for the heat resistance that you see in Samoa. And you mentioned the northern reefs don't have that. Are Hawaii those northern reefs? Or do the Hawaii corals have that or don't have that allele?
It's a difficult question. And I'll say, because we only really know there's a species of tabletop acropora. I don't know if you guys have seen this kind of coral, but it's a beautiful growth form, and I'm only biased because I spent my PhD studying it, right? But it grows up and makes this big round table. It can be huge. If you go to Fongatele in American Samoa, it's just nothing but these huge tables. That's Acropora hyacinthus anyways, one of the taxa that does that. And that's honestly the only taxon where we have well-developed evidence of the genetic basis of heat stress. Acropora hyacinthus does not occur in Hawaii.
What does that say about, I was going to say, what does that say about the strategies that we should try and employ here in Hawaii?
Yeah, it says nothing about that, honestly, because it's data from another place. And, another story. It doesn't say that we don't have them. It doesn't say that we do have them, okay. Right? it is very likely, and really the Ofu pool story, I think, just backs this up. The Ofu pools are not a big habitat, right? It's not like American Samoa is dominated by the corals from these little tiny pools. It's a marginal habitat, but it's weird enough that it sort of selects for the weird stuff in a way that sort of presages what will happen for the rest of it 20 years from now, right? So when you're looking for that, you look for the more marginal habitats. I'll say the best work on this is by a guy named Chris Jury out of HIMB, who compared right here on Oahu corals from Kaneohe Bay and corals from Waimanalo, just kind of right around the corner, right? And what he shows is that corals from Kaneohe Bay, which is a much more variable environment, right? They have big swings in temperature, big swings in aragonite saturation state, that OA metric, right, in Kaneohe Bay, whereas Waimanalo is much more stable. The corals from Kaneohe Bay are a lot tougher. In 2015, corals all over Oahu bleached and died. There was a lot of bleaching that happened in Kaneohe. I don't think a single colony that people were following, they're following hundreds, I don't think a single colony died. They bleached and then they recovered, right? So this variation, right? So if you think about it evolutionarily, the raw material for natural selection starts with variation. You have some colonies, or in my case, what I presented as differential resilience. You have some colonies that can take the heat, some colonies that don't. And the process of evolution is basically selecting for those that can take the heat and moving forward. There is variation here in Hawaii, no doubt. Whether that means that we have all the alleles we need in that same evolutionary model I described, I can't say that one way or the other, but the variation exists.
Okay, thank you.
And I just can't shut up. Sorry. If you look at that annual severe bleaching map that I showed you, not only is there variation in the genetics and the sort of strong coral phenotype, but the predictions on the windward lure side also present this opportunity. Whenever you see that kind of spatial heterogeneity, things are different in different places, it opens opportunity for evolution. I can unpack that if you want, but I hope that's helpful.
Absolutely, thank you.
Okay, we'll get back to the scroll of questions. Quick one on crown of thorns. How do they affect the reefs here? I see them only occasionally snorkeling and swimming, but are they any issue to be concerned of here?
Yeah, I only see them occasionally as well. I've seen a handful of them here and there. The answer is they're not anything to worry about until they are. That's the weird thing about crown of thorns, is that they're just sort of part of the background, and then all of a sudden they are everywhere and they have outbreak conditions. And American Samoa went through one of those outbreaks very recently. I mean, it's now 5 years ago. But they had crazy densities, and they had, teams of folks who got giant syringes full of ox bile and went around and killed them by the thousands all day long for months on end. And they managed to put a dent in the outbreak. Yeah, they're a serious concern. They're also one of these things that, like hurricanes, they've always been there. They're always part of reef ecology. And even the outbreak dynamics is part of reef ecology. But when everything else is going wrong, it's the sort of thing that can, make or break a reef.
And Chris, what else you got? Your hand is up.
Yeah. No, I was just back to the basics. I was just curious. What's the model say if we lose this battle? If we lose the corals, what does that mean for the planet and for the the big picture? I mean, are we totally gonna all be gone if that happens?
I mean, sadly, no. We are a very adaptable taxon. We can take a lot. Will we be diminished for it? Yeah, we will. I mean, coral reefs, just think about pure diversity. Coral reefs, as Cynthia released in the promo for this, they make up less than 1% of area of marine habitats, but they have at least 25% of the species, at least. And recent estimates suggest it's as much as a third to even 38% is the newest one, right? So a huge amount of reef diversity, uncounted diversity, exists in and only in coral reef habitats. And corals, the thing that I study, the actual corals, are the engineers of that habitat. And if they go away, a lot goes away with them. Does it doom the planet? Is it catastrophic? Not necessarily, right? The weirdly, corals are not a major carbon sink, like they're made of calcium carbonate. But because of the weird chemistry of carbonate in water, you could dissolve all the coral reefs today and it wouldn't add to carbon in the ocean, which is strange, right? It feels like it's a peat moss kind of thing where like if you burn the peat, like all of a sudden there's more carbon dioxide, or like you melt the permafrost, all of a sudden there's more carbon in the air. It's weirdly not that for corals, but it still would be, we would be diminished for sure. Sage, you were trying to say something there.
Yeah, I know you mentioned like not moving corals around, but what about the like human assisted evolution? Like I know the Ruth Gates is now the Coral Resiliency Lab. All of that is kind of in that same category with moving corals. Is that something that you think is going to be helpful in going into the future, or not a priority, focusing elsewhere?
I think it's a huge priority, and like I'm super biased though. I was a postdoc in Ruth's lab, and like the idea of the super coral is like a very attractive idea for me. I think it's really important for us to think about it. I think, again, this is an evolutionary challenge, and that kind of thinking is what is going to assist a population to make that evolutionary transition. And I am certainly not saying that, no, we shouldn't do it. Like, don't take that message. My message is it's risky, right? It has high reward, but like what's happening right now in the Caribbean with stony coral tissue loss disease, it's a disease that's ripping through coral populations faster than we can monitor it. They can't even like track it. Like some of the banded diseases that came through Kauai a few years ago, like you could find the colony, you could like scrape it off, you could make some epoxy bands and like prevent it and save the colony. But like by the time they hear there's a disease, they go there, the population is dead, right? So I think it's wildly important to think the way that Crawford Drury and Josh Maiden and the folks who've taken over the sort of torch from Ruth. And if you guys don't know who Ruth Gates is, she's sort of a luminary figure in this whole style of thinking in corals. I think it's really important that we carry that idea through. I think it's also really important that we don't get like overly excited and think it's a silver bullet and do it everywhere without a clear eye towards the risks involved. I hope that's a satisfying answer. Yeah. Okay.
Yeah, that kind of summed up most of what I was trying to get at there. Thanks.
Yeah. Sure.
Can you talk about, Tom, sunscreen for just a few minutes?
Yeah.
And
Yeah,
I know there's
I
a
can.
lot of people in Hawaii, and there's been legislation recently, and
Yeah.
Reef Safe and all of that. What are your
I'll
thoughts?
say my thoughts are it's an inspiring story of action, right? In that it went from a couple scientific papers. There are two papers, at least the ones that I've read and know about, that identified avobenzone and oxybenzone as potentially involved in affecting reefs, corals physiologically, right? And basically suggesting that one paper said that it might affect their bleaching threshold, they might bleach more if exposed to it, and the other one suggested that it's detrimental to larvae, right? And we went from that to banning those substances. And frankly, that was exciting and inspiring, right? Both in that we did it, that it got it done, and I think the science is sound, right? That like the trials that he did do what he says they did. I guess the like, but you can hear me trying to formulate correctly is, but I wish we had the same burning fire for cesspools. I wish we had the same burning fire for, you know, robust and, you know, sustainable and productive fisheries management. I wish that same passion that backed up that drive would spill over. And I think it is, right? And the important thing is that it's not a zero-sum game, this whole thing. Like, passion leads to passion, fire leads to fire. And if that fire starts with sunscreens and spills to cesspools, awesome. I'm all for it. I should say I got to be really careful with some of this stuff. I am a federal employee and I am bound by the Hatch Act, which means I really can't talk about policy that directly. So I can tell you personally what I think about stuff. I can't make recommendations for policy. So I'll say, yeah, what I said, but just keep that in mind.
Very well said. Very well phrased as well. And so speaking of being a federal employee, one of the questions on here was simply, how's your budget prospects? And I'm not sure what exactly that means, but
I think I know what it means.
Okay.
I can remember that one. I mean, basically, I'm going to interpret that as saying we have a new president. The president's administration has a new focus on climate change, which is at the heart of much of my science. And the president's budget landed last week. So there's a lot of talk about how my budget prospects are looking, or really our collective federal employee budget prospects of those folks who study climate. Unclear is the strongest answer. You don't get money without a clear plan is the shortest thing. And so we're right now trying to mobilize some plans. The biggest stuff, I think the biggest push that we're doing is really trying to collect more data, turn data into information faster, turn that information into models where we can try out scenarios in the future that are relevant to decisions that actually have to be made, right? That sounds pretty simple, but getting the data over the spatial scales that we work is very hard. So we're right now looking at major investments in tech to do that, right? So it's not just all underwater humans, but so that there are underwater robots collecting imagery. When you collect imagery, it means a lot of like circling stuff on a computer screen for a lot of humans stuck in that facility that I showed you a picture of. And that's super slow going work, right? So we're investing a lot in machine learning tech. That takes money, it takes effort, so that we can turn the imagery into coral growth rates faster. We're also investing in a whole bunch of modeling so that we can turn coral growth rates into coral population growth, right? And evolutionary models. And let's try out all of those things that we listed that are high reward but high risk. Try them out on a computer in a simulation model before we actually move corals around and potentially, expose everybody to disease. So there's a lot of stuff, especially sort of the more tech supporting stuff there, that I think we may benefit from given the climate focus of our research. But it's really unclear and none of it has really landed yet. It's early. The bigger deal, frankly, is the reauthorization of the Coral Reef Conservation Act. And if you, well, I'll let you guys interpret action as you see it, but that is ongoing. That is on the bubble, and it is a bipartisan push with a Republican senator from Florida and a Democratic senator from Hawaii that don't see eye to eye on lots of stuff, but they're carrying this through, and it seems to be moving. That is also going to change sort of our stance as a nation in terms of the problem. That's no longer called the Coral Reef Conservation Act. It's now called the Restoring and Maintaining Resilient Reefs Act. Right. So that idea of resilience is even making it to the core legislation that funds the kinds of stuff that I do.
Great. Good answer to that question. And I see we just got a few minutes left here, but I want to add two questions together. Sort of, Joanne was asking about the local. And
those will be our last ones.
Yeah, the local tools. So although you don't make policy recommendations, but keeping water clean, keeping the herbivores around, any other particular local tools that we should think about here on Kauai, and what can we do individually here on Kauai and throughout the islands to help coral reefs? So.
Well, I mean, I'll start with the one of the things that my favorite things about that model that I told you about with the genetic alleles and the evolutionary model is that I think it backs up my general intuition. A lot of these problems, we got to do both. It's a both and problem. It's not an either or. We got to mitigate global climate change, right? And we have to take aggressive action on a local scale to put our reefs on the best footing for that. Being more specific about what our reefs like being on the best footing is definitely being concerned about water quality is important. Being concerned about fish, is important. In your personal lives, just, I don't think like an ecologist, know where your stuff is going, right? One of my favorite things that I ever did when I first moved to Oahu is I took the tour de trash, and they tour you around Oahu and they show you all the waste management facilities, right? And just having that kind of sense for where are the ins and outs of my life and how could they be affecting reefs, I think is really helpful. I will also add, though, especially around climate, individual responsibility is not the end of the story. There is institutional structures that we need to pay attention to in our lives and in the lives of our planet.
Okay, that's a really good note to end on. And it's a little hard to bring this to a close. Yeah, I see. Great final question, as Alana says there in the chat. So, and somebody reached out to me to ask, where could you get a recording of this? Tom, this was, if you don't know, this was fabulous. I did see the dry run, and Tom can go lots of ways. And I really appreciate how much he consolidated such a fact-filled, interesting presentation for us. So there will be a recording of this. I'm going to send it on to my kids, and it's going to be on the Zero Waste Kauai page for all of you to find. And with that, we're going to say goodbye. So you can just unmute or use your reactions, and let's thank Tom for spending his time with us.
And we try to have the recording in two places. One is on the Zero Waste Kauai Facebook page, and the other one is the Vimeo, Zero Waste Kauai Vimeo page. So both of those.
Forgot that part. Yeah.
Okay, sorry, my daughter just got home from swim class. She didn't want to say hi to everything. She's wearing her swimsuit, but that's okay.
Thank you, Tom. Thank you guys for coming. It's a good show. See you next
everyone.
time.
Bye, guys.
Thank you, everyone.
We'll get you the rest of these questions. There's a few more that we didn't get to. Some technical stuff.
Okay. Awesome. And I saw there was a bunch of like reaching out for networking as well, and we're happy to do that. That's part of what we do is supporting tech. And whoever, I know we didn't get to their question, but I think maybe it was Scott was talking about coordinating with Hawaii DAR, and Heather at Hawaii DAR is a great colleague of mine. She's wonderful. So I would certainly say get in touch with her. So yeah.
Great.
Oh, look at that. There's the Vimeo link already.
Well, we're still recording. How's that working?
Oh, I don't know. Maybe it's a different Vimeo link.
Oh, I see we had one of our